During this video I'm going to be talking about reflection and also waves passing through boundaries, so boundary transmission. I'm going to think about it in a series of important features I'm going to try and bring out. First of all, I'm going to quickly talk about the distinction between what a wavefront and a ray diagram is. Just some subtle nuances there. Consider the rules of reflection. Then consider reflection of a string on a fixed and non-fixed ends. And finally, identify reflection at boundary changes and actually transmission as well. So there's things I'm going to talk about during this session. Let's start off with job number one, the idea of wavefronts and a ray diagram. This diagram is kind of a diagram of reflection. What we see here is the arrows are good examples of a ray diagram. A ray of light is shown as a clear straight line hitting the boundary and reflecting back off at it. We'll talk about the rules with that later on. Now, ray diagrams, we also have some wavefronts. Now, what's happening here with these wavefronts, it's not possibly perfect, but we're showing that at each wavelength we have a whole line of waves working together or going along at the same motion, so reaching at the same point at the same time, and how all of them go through reflection, so that means all of these wavefronts will be running aligned with each other as we go through. The idea of a wavefront, and if I just go to a little bit more detail now, wavefront propagation works on the idea, it's kind of Huygens principle. That's the idea that at every single point on the wavefront acts as an independent spherical wave spreading out. And that independent spherical wave spreads out, and it happens that all of the spherical waves will line up again one wavelength later to create another plane wave. This works in a similar fashion with circular waves as well. What you'll see is that spreading out is caused by considering every single point on the wavefront to be a single wavelet, is the terminology we like to use, spreading out in a circular fashion, and then one wavelength later they're all aligned and we're able to draw another wavefront. So that's that. I'll talk about reflection now. I'm going to talk about reflection, and I'll be using just a simple ray diagram. The idea of reflection is, if I have a mirror, which is a common reflecting object, to start off with I have to consider what's known as the normal. And the normal is an imaginary line at 90 degrees to the surface of the mirror. A ray of light will approach the mirror, and that's known as the incident ray. It will strike the mirror and reflect off, and that reflected ray is obviously known as the reflected ray. Now, the rules of reflection mean that if I consider the angle between the incidence ray and the normal, that's known as the angle of incidence, and in turn the angle between the normal and the angle reflected ray is the angle of reflection. Now, this rule, or the rule which dictates reflection, means the angle of incidence equals the angle of reflection. Something I'm quite sure you've come across many years ago in your own learning, somewhere along the state. So now let's think about another type of reflection. This time we've got the reflection of a pulse travelling along and coming to an end. Okay, so we have a boundary point. In this case I've got two options. One option, I've got a reflection taking place at a fixed end, so that means that the string is tied onto the piece of wood, and I've also got reflection at a free end. Now what happens here, and I guess it's shown best visually, and I'm going to click across to my first diagram. Here we see when we have a pulse hits a fixed end, what happens is it inverts. So it will reach the boundary point and then invert and reflect back again. So another form of reflection. Whilst if I have a non-fixed end, what happens is the pulse will come along, and because of the non-fixed end it means that I don't get that inversion. The wave will just reflect back again across through the medium. So, reflection at a fixed end, a phase change occurs, which means it's inverted, and at a free end no phase change occurs at all. The final thing to think about is waves transmission. So this is when we go from one medium to another. A denser medium to a less denser medium, in some cases, or a more dense to a less dense medium. Either way round, what happens then is kind of interesting. And what we can see with this diagram here is we get two things taking place. At the boundary, I get part of the wave continues on, so that's transmitted, but part of the wave is also reflected back again. So we've got to think about the rules which are related to that. Now, those rules, I guess the summary of those statements. No matter what happens, the wave speed is always greatest in the least dense medium. That's for all the waves. The wavelength is greatest in the least dense medium. The frequency of the wave is not altered when crossing the boundary, so that doesn't change in any way. The reflected pulse becomes inverted when a wave in a less dense medium is heading towards a boundary of a more dense medium. And in my diagram here, what we can see is the wave that's approaching this boundary has a positive peak, followed by a negative trough, and when it goes back again, it's led by the trough and followed by the peak. Okay. And the other thing to note is that the amplitude of the incident pulse is always greater than the amplitude of the reflected pulse. Now that means that because there's been some energy transmitted, that means that the amplitude is going to be reduced down. So those are the key ideas about reflection, wave fronts, ray diagrams, and also the transmission across a boundary. There's lots of quite technical terms. It's worth going back through and trying to make sure you've extracted your key ideas there.